Okay, here we go. This is part 2 of antiderivative notes. And if you're doing book problems, you'll see there's a ton of antiderivatives and you should practice lots of them. That's going to be our life this quarter, is finding antiderivatives. So the more we do, the better we're going to get at them. So there's a fair amount of trig antiderivatives in this section of the book. So what I would say here is if you get a trig antiderivative, a trig integral that looks kind of strange, don't be afraid to use trig identities. This is a quotient. I know I can't just take the antiderivative of the top and the bottom. That wouldn't work. So what I would do is just start changing everybody to sines and cosines. So I'm rewriting cosecant 2 theta as 1 over sine 2 theta. Again here, minus sine 2 theta. So I'm changing everybody to sines. What I'm going to do next is find a common denominator. This one top and bottom by sine 2 theta. Maybe I could actually write it here. So that will give me 1 minus sine squared of 2 theta, all divided by sine of 2 theta. Now I have a fraction divided by a fraction, so we can flip and multiply. The sine 2 thetas cancel out. And using a trig identity here, 1 minus sine squared of 2 theta, remember that's equal to cosine squared of 2 theta. So all of this could now be written as 1 over cosine squared of 2 theta. And remember, that's also known as secant squared of 2 theta. And secant squared is, of course, tangent's derivative. But what we were practicing on the last notes was there's a little bit of a chain rule here, right? We have to acknowledge a chain rule in reverse. The antiderivative of secant squared of 2 theta is tangent of 2 theta divided by 2, which is the same thing as times 1/2 plus a constant. Okay. And another quick example, in fact, just to integrate tangent squared theta by itself, you would actually use an identity for that. Okay, we were doing these identities. Well, I think we used some in 21A, but anyhow, tangent squared theta plus 1 equals secant squared theta. That's a pretty well-known identity, which means tangent squared theta could be rewritten as secant squared theta minus 1, so 2. And that's exactly what we're going to do. To integrate tangent squared, we're going to rewrite it as secant squared theta minus 1. The antiderivative of secant squared theta is tangent of theta. The antiderivative of 1 with respect to theta would be just theta, right? Plus a constant. All right. Now, there's also a fair amount of problems like this in this section of the book, and it's a good reminder. So the question is simply, decide whether this secant cubed theta over 3 is the correct antiderivative for tangent of theta times secant squared theta d theta. So now, one way to do it, of course, would be to try to find this antiderivative and see if you get that. But for these types of questions, they're not really wanting you to do that. Instead, this is a good reminder of how do we know if we have the correct antiderivative. What we can always do is take the derivative of this and see if we get that, right? We couldn't check our answers that way last quarter, but we can this quarter. So the way to approach this is to take the derivative and check. And so that's what I'm doing here. Remember to take the derivative of secant cubed theta. You may want to rewrite that as secant, but it's the whole thing cubed. And so this is a chain rule. Bring the power down, stuff to the second power. Notice the 3's will cancel. And then by the chain rule, you have to multiply by the derivative of the inside, which is secant theta tangent theta. If I put everything together, I'm going to have a secant squared times another secant will give me secant cubed theta times tangent of theta. which is clearly not the same as this, what was inside the integral. So that means this is not the correct antiderivative. Let's try another one. And let's get this focused. There we go. All right, so what we want to check to see is if the antiderivative of inverse tan of x over x squared is this whole mess on the right side. And so the way we're going to do that, if that's f of x, we're going to take the derivative of this and see if we get that. So this might be a good time if you want to practice, pause the video and go ahead and work it out. Try to take the derivative of this and see if you do get that. All right. So if you paused, we'll come back, and it is a bit of work. These notes, again, are the same notes on my website, so you could check this out later and go through it in more detail. But if you work this out, you should have seen that it actually does work. There's a bit of simplification you have to do with a couple of these terms. You have to find a common denominator and cancel some things out, but it actually does work. So that is the correct antiderivative. Okay. Moving on here. So another situation where we use antiderivatives is to solve what we call initial value problems, also known as differential equations. Many of you in the engineering and math field, if you're taking 21B right now, you know you're going to be going on, and there is a course called 22B here at UC Davis, which is all about differential equations, solving equations that involve a derivative. There's a whole course on it because they do get complicated. So this is kind of an intro to that. So we know that the derivative of some function r with respect to theta is cosine of pi theta. And we have, this is where the initial value comes in. This tells us when, okay, theta is equal to 0. When theta is equal to 0, that's a theta, then r equals 1. And so we're going to use that information eventually. But right now what we want to do is to make sense if the derivative of r with respect to theta was this, and we want to solve for r, we should find the antiderivative of cosine of pi theta with respect to theta. And that's a reverse chain rule. Antiderivative of cosine is sine of pi theta. We're going to divide by the derivative of the inside, which is, as long as it's a constant, which it is, which is pi, plus c. So what do we do? The additional step with this is we're going to plug this information in to solve for c, because we know that when theta is 0, r should come out to be 1. So I'm plugging in 0 for theta. That's going to make this inside equal to 0. And plus c, and set the answer equal to 1. Sine of 0 is equal to 0, so this part gets wiped out. My constant of integration in this case is 1. So my final solution, what I do is I just take that constant and put it right back in to r of theta, and that is my solution to this initial value problem. Let's see what's next. Oh, okay. Now, whoa. So particular to most of the students, if you took 21A last quarter, the professor skipped the derivative examples having to do with velocity and acceleration. But you're going to probably see these again even in 21B. So what we have is a rocket taking off with a constant acceleration of 20 meters per second squared. And we want to know how fast and how high the rocket is after 1 minute. So the idea here, there's a little bit of physics involved, and this is where it would have helped if we had covered this in last quarter in 21A. the acceleration in physics, acceleration is the rate of change of velocity, which means it's the derivative of velocity. So we're given the acceleration, which is the derivative of velocity, is 20. If we want to know how fast the rocket's going, we're going to want to know the velocity. So if this is the derivative, we're going to want to take the antiderivative to find the velocity. So we do the antiderivative of 20 with respect to t. That's a constant, so it's just going to be 20t plus a constant. We're also going to want to know how high the rocket goes. So we're going to want to know the distance, how high it goes, which is going to be the antiderivative of velocity. So we're going to need to integrate this again, but we want to know what that constant of integration is. So we have to read into the problem a little bit. The previous problem, remember how we solved for c, was we plugged in some information about our function. In this case, we'd want to know, what do we know about the velocity of our rocket at some time t? Well, the problem says the rocket takes off. So that kind of implies that the rocket had a zero velocity at the beginning when t was 0. So we're going to assume that the initial condition v of 0 is equal to 0, and we're going to plug that in to solve for c. So we plug in 0 for t, and that of course is 0. So what happens is, in this case, my constant of integration is actually 0. So my velocity equation is just 20t. And as I mentioned before, that is actually the derivative of position or distance or height of the rocket. In physics, it's kind of customary to call the position function s of t. So that's why I wrote that as ds dt. It's the rate of change of position. So we're going to find the antiderivative one more time to find our position function. So we're going to integrate 20t. That's going to be, remember the power rule, the constant stays there. Add 1, divide by the 2. That's going to give you 10 times t squared plus another constant. How do we solve for that constant? Well, what do we know about the height of the rocket when t was 0? Again, since the problem said that the rocket took off, we're going to assume that the height of the rocket was 0, that it was on the ground at the beginning when t was 0. So we're going to assume our initial condition is s of 0 is 0. We'll plug that in, put in 0 for t. Once again, we get a constant of integration equal to 0. So my position equation is 10t squared. Now we have a velocity equation and a position equation, so we can start to answer our question. Question said, how fast is it going after 1 minute? And how high is it after 1 minute? Going back, I'm going to slide this back up. The information for acceleration was given in terms of seconds. So after 1 minute, that would be 60 seconds. And so we can just plug 60 in for our velocity and our position, and we get a velocity of 1,200 meters per second and a height of 360,000 meters. Okay, I'm going to close this video, and we'll probably start the next section on the next video.